Hi, my name is Chris Bishop, and I'm here to tell you how carbon-based life forms can prospect for gold without fear of melted or radioactive dishes. Now, by carbon-based life forms, I mean people, and you might think it odd that people who are looking for gold would have a problem with radioactive dishes, but I assure you that radioactive dishes could be a problem. All life on Earth contains carbon as a main building block. This is what it means to be carbon-based. The carbon is a main ingredient in building the molecules in our bodies. Carbon is often represented by the letter C, and we have H, O, and N for hydrogen, oxygen, and nitrogen. Since we eat things that were once alive, our food contains mostly these four elements, but also trace amounts of just about every other element. Remember, you are what you eat, and your body contains roughly 0.0002 grams of gold. If you take a nickel and divide it into 25,000 parts, that's about how much gold is in your body. That much gold is worth about 1 cent. Although the amount of gold in your body is small, every plant and animal gets its nutrients from its environment. This suggests a way to find a large amount of gold. First, test the leaves of trees and plants from various areas known to have at least some gold. You want to measure how much gold is in the leaves. If you find larger amounts of gold in plants from certain areas, return to that area and dig there. It stands to reason that where there is more gold in the leaves, there is more gold in the ground. Perhaps you could strike it rich.
Excuse me while I start my tea. I like sugar in my tea, so I have some sugar in a stir. First, I'll put some sugar into the water, and then I'll use my stir to stir it together, and in a minute, I'll add the tea. Okay, we'll just let that sit.
Okay, you might wonder why carbon is the basis of life and not some other element. The answer is that carbon has the ability to connect itself in many ways. For example, in chains. Here I show octane, which consists of 8 carbon atoms in a row surrounded by hydrogen atoms. Gasoline contains octane. The sticker on the pump indicates how much octane is in the gasoline. Carbon can also connect itself in rings, or sheets, or tubes, or even spheres. Trees can stand tall because carbon can connect itself in these many ways. Most other elements cannot connect like that. Many scientists think that all life everywhere in the galaxy must be either carbon-based or silicon-based. Why silicon? Since silicon is under carbon on the periodic table, it should have some of the same ability to connect in different ways like carbon does. However, as you go down the column, the sizes of the atoms get bigger, so the ability to connect and other properties change. By the time you get to the next element, germanium, the properties have changed enough that it would be difficult for life to form.
Oh my goodness, my stir melted. The stir was made out of gallium. I forgot that you only use gallium for cold things and not hot things. See, gallium melts at 86 degrees. So when I put it in the hot water, it melted. But that's okay. I can just make it again. So first I'll put a placemat down in case I have any spills. Then I'll pour off the hot water. And there's the gallium at the bottom. And I'll soak up any extra water with the paper towel. That's about got it. And now I have to have the mold for the stir. It cooled a little bit there. Okay, I'll just spread this out a little bit. There we go. And now it actually takes gallium a long time to cool down. So what I can do is put it on ice. So it only has to cool down to 86 degrees or 85, but it will go a lot faster if we put it on ice. We'll just set it there and leave it for a little bit. We'll come back and see what it looks like later.
I especially made the stirrer out of gallium, which is right here under aluminum and next to germanium. Since it is under aluminum, you might expect it to be kind of like aluminum. It is, but it melts at just 86 degrees Fahrenheit.
It's 15 minutes later, and it's partially solid, but not all the way solid. You can see it wiggling. Okay, now it's been 30 minutes, and it seems pretty solid. Let's see if I can get it out of there. For that, I can stick in a screwdriver, pop it out. So now I have a new stirrer that I'll use only for cold beverages.
You may be familiar with mercury, which is liquid at room temperature. Gallium is similar, but unlike mercury, it is not dangerous to people. Although I use gallium for the stirrer, most people make their utensils out of silver, aluminum, or steel. Steel is made from carbon and iron. Kings might also use gold. Napoleon III, ruler of France, would serve as most honored guests with aluminum forks and knives. Although aluminum is very cheap today, at his time it was worth more than gold.
Excuse me, William Arium, the elementium's namium for you?
That's an excellent question. Elements are often named after places. In the United States, a lot of elements were discovered using the equipment at the Lawrence Berkeley Lab in Berkeley, California, America. From that we get berkelium, californium, and americium. Livermorium was named for the nearby town of Livermore, California. Here's my family and I at the Lawrence Berkeley Labs. The machine behind us smashes together atoms at high speeds. Another country with a lot of elements named after it is Sweden. Here is Stockholm, Sweden. And nearby is Ytterby. From Ytterby, we get yttrium, terbium, erbium, and ytterbium. Why Ytterby? Many rare elements were found at a mine there. Also, from the city Stockholm comes the name holmium. Here are other elements named for places in Russia, Poland, Germany, Denmark, Italy, France, Scotland, Greece, Scandinavia, and Europe. Many elements are named after people. Here we see Albert Einstein, Alfred Nobel of the Nobel Prize, the famous Madame Curie. Here's Lee Meitner. Over here is Glenn Seaborg pointing at the element named after him. Oh, and down here is William Röntgen, who took the first X-ray. All these people have elements named after them. These elements were named after gods, moons, planets, and the sun. For instance, Mercury, Thor, Uranus, Neptune, and Pluto are all gods. Here are elements named after their colors. Gold comes from the Old English giallo, which if you change the G to a Y, almost sounds like yellow. Yolo, yellow. 3 elements have names that mean something like hidden or hard to get at. 4 were named after other elements. And 5 elements were given names before people knew what elements were. Those old names are what people still call them: sulfur, iron, silver, tin, and lead. And since a lot of elements are found in rocks, it makes sense that some elements are named after rocks. Bromine and osmium are named for their smells. I heard that Glenn Seaborg chose the symbol Pu for plutonium because of its smell. Pu. Of course, some radioactive elements get their names from their radioactivity. And there are a few more elements with names meaning various things. Now I'm going to talk about radioactivity. But first, we need to know something about atoms. Atoms are made of protons, neutrons, and electrons. Protons and neutrons are about the same size, and electrons are smaller than protons and neutrons. The number of protons determines whether an atom is hydrogen, helium, or some other element. If an atom has 2 protons, it is a helium atom. A helium atom usually has 2 neutrons and 2 electrons also. And when we talk about radiation, there are 3 types. Alpha particles are made of 2 protons and 2 neutrons, like a helium atom but without the electrons. Compared to beta particles, an alpha particle is very large. Beta particles consist of just an electron. Since beta particles are smaller than alpha particles, it is harder to stop them. Finally, gamma radiation is a ray, such as an X-ray. Everybody knows that uranium is radioactive. It is used for bombs and also for dishes. Uranium once was used to make the orange color, but not anymore. Here are some other radioactive elements. Americium is used in smoke alarms, and thorium is sometimes used in welding rods. Radiation can be measured with a Geiger counter. A Geiger counter counts how many radioactive particles hits it every minute. Once I took a Geiger counter on an airplane. Here you can see when the Geiger counter passed through the X-ray machine. Then you can see the portion of the trip from San Francisco to Los Angeles. Finally, you can see when we took off from Los Angeles and landed in Nashville. The radiation is higher in an airplane than on the ground because the radiation comes from the sun and is blocked by the Earth's atmosphere. On the ground, more radiation is blocked. Because the radiation is a little lower on the trip from San Francisco to Los Angeles than on the trip from Los Angeles to Nashville, I can tell that the plane was flying lower. Let's measure the radiation from a uranium plate. How many sheets of paper does it take to block most of the radiation? I'll measure the radiation with no sheets of paper.
And I'll measure it with 10 sheets.
Then you can come up and add 10 sheets of paper at a time and measure the radiation. We'll make a graph of how the radiation changes as paper is added.
Okay, so I'm going to measure the background radiation. And here's my meter. And right now it says 5 counts per minute. 11. So it changes because it measures a few more, sometimes it measures a few less. There's an 8. Okay, the sensor's here. So I'm going to measure upside down because I'm going to put a plate underneath this. So it's at 17, 11. So somewhere around 11 or so is the background radiation. So now I'm going to bring the plate. And I'm going to just measure the plate. So it takes it a few minutes to get the counts, but every time that light lights up and it beeps, that's another detection it's making. So it's adding all theirs up. And so right now it says 396 CPM is counts per minute. So it's up to 526. How do you think it can go here? 607. 592, 619, 637, 673, 697, 682. So somewhere in the high 680, maybe 680, something like that. So I'm gonna put one stack of paper. This is 10 sheets of paper, and it's going to block some of the radiation. It's going to block most of the alpha radiation. So what we're measuring now is mostly beta particles. So it's dropped to 459. It's still dropping. 351, 366, 348. So maybe about 350 is a good number. Okay, so now I'm going to call different people up, have them measure the radiation. We'll keep adding 10 sheets of paper each time. Okay, so who would like to go first? That's it. Step over this way.
20 sheets.
Hey, are you two brothers?
30 sheets.
Triplets? In the same class?
40 sheets.
I don't think it's pajama day.
50 sheets.
Did you go already?
60 sheets.
You must be the oldest brother.
70 sheets.
Wait, who are you? Wait, who are you?
'80 sheep.